In section 10.3, we want to discuss infinite series a little bit more. In particular, we're interested in two types of series, the geometric series and telescoping series. We'll spend a lot more time on geometric. Telescoping is kind of a minor point. All right, so let's talk about geometric series. Now remember, we had a geometric sequence. Let me bring that up. A geometric sequence was anything that was, technically you'd have a times r to the n, where a is a constant. But you have some ratio raised to a power. And then you can see that that sequence converges if -1 is less than r, which is less than or equal to 1. See the solid line over here. And then it diverges when r is greater than 1, and it diverges when r is less than or equal to -1. That's for the sequence, the list of numbers. Now we're going to talk about the series, which is when you're adding that list of numbers, when you're going to sum them. So you'll notice we are going to sum. So we're going to take that geometric sequence, which is a times r to the n, and we are going to add up all of the terms of that infinite sequence, and it makes an infinite series. It starts at the 0th term, and then it ends at infinity. Right there. All right, so then when will this converge? And it's a slightly different picture than the other one, but be careful. They're very similar, and students can get them confused. If it's in this region right here, which is -1, which is less than r, which is less than 1. Now notice, there's no solid line over here at 1. The sequence converges at 1, but the series does not. So it has to be between -1 and 1. If it is in that region, if r is in that region, it will converge. It will converge in a particular to a particular formula, which is right here. So if r is less than, the absolute value of r is less than 1, then that series is equal to a divided by 1 minus r. And you can read your book for proof of that, but that is in fact the case. A being the constant, r being the ratio. If r, the absolute value of r, is greater than 1, which means either it's over here, positive, right, +1 or higher, or over here, -1 and less, then the series diverges. Period. The end. That's how it works. So geometric series are nice because they work in a very particular pattern. And this theorem is establishing that pattern. And again, for a proof of it, feel free to read the book. Okay, so if that's the case, then we can use that to answer and evaluate the following. So we can evaluate the following series if they converge. If they converge, we will know what they converge to by virtue of this formula up here. And if they diverge, we'll be able to know that also. So let's look at this first one. This is 3 over 2 to the n. So let me rewrite that really quickly. That would be the same as the series from n equals 0 to infinity of 3 times 1 over 2 to the n, which is the same as 3 times, oh, sorry, I forgot my summation notation. Series n equals 0 to infinity, 3 times 1 over 2 to the n. Because 1 to the n is 1 no matter what, and 2 to the n is 2 to the n. So those are equivalent forms. But if that's the case, then we can actually see our values right here. That is a. Right? A is 3. And my ratio, r, is a half. Now, a half is in this region of convergence. Therefore, this formula will work. Therefore, this particular series will become a over 1 minus r. A is 3 divided by 1 minus r, which is a half. Well, 1 minus a half is a half, so that's the equivalent of 3 divided by a half, which is 3 times 2 over 1, which is 6. So this infinite series right here is equal to the number 6. Even though it adds forever and ever and ever and ever. Even though it's 3 times, right? Well, it's 3 for the first term because you put in 0. A half to the 0 is 1. So it's 3 plus 3 times a half, which is 3 halves, plus 3 times a half, which is 3 over 4, plus 3 over 8, plus 3 over, right? That's what you're doing. So it's 3 plus 3 halves plus 3 fourths plus 3 eighths plus forever. All of those numbers added up will make 6, even though it goes to infinity. Geometric series are amazing things. Now let's look at letter B. So the A in letter B, you can see I have 3 over 2 to the n power, which means the A is right there. And since I don't see it, it must mean that A is equal to 1. Right? There's a constant there, and it's 1. And then my R is rather obviously 3 halves. Right? They're not the same because in this one, this was 3, just 3, right? It wasn't 3 to a power. Whereas here I have 3 to a power. But if R is 3 halves, that is greater than 1, therefore this diverges. So this series diverges. All right, what about letter C? Well, I rather obviously have 5 right here, so that's my A. A is 5. And then my R is negative 2/3. Okay, well that's less than 1, so this is going to be convergent. Oh, I should have mentioned that. This is convergent, right? If you get a number, if you're evaluating it, it's converging. All right, this one's also going to be convergent because negative 2/3 is over here in this side, right? It was still in the convergent zone. All right, therefore, it's going to be, oh, sorry about the dog barking. 1 second. It'll be A over 1 minus R. A is 5 divided by 1 minus, but my R is negative, so it's going to be a negative 2/3. Okay, well, that's obviously 5 divided by 5/3. Because 3/3 plus 2/3 makes 5/3. Which would be 3, because it's 5 times 3 over 5, which is 3. All right, so that one is obviously convergent. Last but not least, in this particular one, A is negative 17, which kind of is irrelevant because you can see that R is negative 1.04. And that's a problem because negative 1.04 is over here. Well, not that far, but it's over here. It's less than negative 1. So the absolute value of R is greater than 1. Therefore, this is divergent. I guess I could just write that here. Greater than or equal to 1. By the way, for the record, for greater than or equal to, we can write it this way with a flat horizontal line, or you can write it this way. Either one's valid. I tend to write this one when I'm writing by hand.